Assalamu alaikum. How are you, my dear students? Hope you will be fine and okay. I welcome you all into my today lecture. In today's lecture, we will study the conversion of. We will study the conversion of galvanometer into ammeter, voltmeter, ohm meter, and then at the end we will study the ammeter also. Now, in my last lecture, I told you about the galvanometer, and I told you that galvanometer is the most sensitive instrument or device which is used to detect and measure a small value of current or potential difference in a circuit. So you see in my hand, and this is the galvanometer, and this galvanometer is for the various range, right? And you see the terminal of the galvanometer also. And I told you that if you want to measure or detect the current in the circuit, then galvanometer will be connected in series within the circuit. So you have to break the path for inserting the galvanometer. And if you want to measure the EMF of the source or the terminal potential difference, then the galvanometer will be connected in parallel across the device. Now, beside this, I told you that the galvanometer, it has one disadvantage also. And what was the disadvantage of the galvanometer? That it cannot measure the current of more than few milliampere. That was the limitation of the galvanometer. So it is not always that we will measure small value of current or potential difference. Sometimes we need to measure large value of the physical quantities. Then for this purpose we will use the ammeter, right, to measure the large value of the current. So in my hand, this is the milliampere galvanometer, but still on the scale you see it is from 0 to 100 and from 0 to 500 milliampere, which is very large as compared to the reading by the galvanometer. Now the question is that how to convert the galvanometer into ammeter. So ammeter is in fact the modified form. It is the modified form of galvanometer. It is what? The modified form of the galvanometer. Here, instead of the true diagram of the electronic diagram of the galvanometer or the ammeter, better that we will use the symbol, the electronic symbol of the galvanometer. So the symbol for the galvanometer is, this is the galvanometer, this is the ammeter, and this will be our voltmeter, right? Now, how we can convert or modify the galvanometer into the ammeter? Galvanometer, the can be galvanometer can be converted into the ammeter by connecting a small value of resistance, a small value of a resistance called shunt resistance in parallel with the galvanometer. Shunt resistance, and for simplicity I will write RS, shunt resistance, in parallel with the galvanometer. In parallel with the galvanometer. In parallel with what? In parallel with the galvanometer. Now there are few things. First, why the resistance why the resistance has a small value, right? Why a small value resistance, which we call the shunt resistance. One, this thing. And the second important point, that why in parallel, right? So when I draw the diagram, then hopefully you will get answer to these two questions. And the third question is that what is the value of this RS? So in order to convert the galvanometer into the voltmeter, then as I told you that we will connect a resistance called the shunt resistance in parallel with the galvanometer, as you see. So this is the galvanometer, right? And we are going to connect a resistance called the shunt resistance in series with the galvanometer, as you see it. This is called the shunt resistance. Let this be at the point A and at the point B. And then we supply a potential difference, it is connected within the circuit with some EMF source V, potential difference source, right? This will change the galvanometer into what? Into the voltmeter. So this assembly together form what? The ammeter, as you see here. This is our ammeter, and this should not confuse you, class, that you ask that, or if you think that I have connected the shunt resistance with the galvanometer in parallel, don't confuse this thing that I am measuring the current, right? For measuring the current, whether it is galvanometer or whether it is ammeter, it will be connected in series with the resistor, with the appliance, or with the EMF source, right? This is the construction or the conversion of the galvanometer into the ammeter. It is not that we are using the ammeter, so you should make difference between these two statements, right? Now let us label this, that if the current it is going to supply, the source current is I. Clear? Now you know that parallel circuit is current divider. Parallel circuit is what? It is the current divider circuit. The current divider circuit. So in the this kind of situation here, what is going to happen, that the current will be divided, right? As let I suppose that the resistance of the galvanometer is Rg. This is the resistance of the galvanometer. So the amount of current that pass through the galvanometer will be what? It will be Ig. And the current that pass through shunt will be the Is. And if you see class, since the current that pass through the galvanometer is known, it is Ig. And then what will be the shunt resistance? And then the shunt current will be the total current I and minus the galvanometer current Ig. Now you will be asking that whether it will be known. This is what our supposed current. For example, if I want to convert the galvanometer into the ammeter which can measure a current of within the range of 10 ampere, so this will be then 10 ampere, right? So that is the shunt current which pass through this one. Now ideal ammeter should have what? The ideal ammeter should have smallest resistance, so that because it is always connected in series, then therefore all of the current should pass through the galvanometer for measuring the current in the circuit. Now you see here, look, as I told you that we connect the ammeter in series within the circuit to measure the current. So we kept the shunt resistance, or we have chosen a resistance of very small value. Why? Because when you connect it within the circuit, the ammeter, this is the interior structure of the ammeter. So you know that when there is a large current, so since current always choose the path of least resistance, this is the basic principle of this chapter, right? As I usually told, that current always choose the path of what? The path of least resistance, right? So the resistance of the shunt must be smaller than the resistance of the galvanometer, very small. So this is why the large current will be bypassed and only limited current will be allowed to pass through the galvanometer. That limited current will be how much is how much. So for this, that little current will be in the safe range, so that the galvanometer needle should not give a full scale deflection, more than a full scale deflection, and get damaged. Right now the question is that you will be asking, sir, what is then the use of it, that if it bypass, right? First of all, there is a scaling. This is done for the known current first, right? So that is very easy and very simple. First, you will do it for the known current. For example, if you just see the dial of the galvanometer, for example, and at a point when you apply, for example, a known current of 10, let's say, for example, first you do it for the known current of 5 ampere. So the galvanometer needle will stay somewhere, for example here, right? So what you will do, you will write a 5 ampere, right? We don't care that how much is passing through it, but where is the galvanometer needle stay, we will mark it as 5 ampere. Then we will do it for the 10 ampere. Definitely 10 ampere will be more than the 5 ampere, like that. And the galvanometer needle will stay somewhere here, and we will mark it as 10 ampere. And this distance and then divided into equal parts, right? And definitely it will be in between 5 and 10 milliampere. So that is what a scaling. So this is not the situation where why it is going to bypass. Clear? So this is one of the situation here. Now, our interest lies that what could be the appropriate value of the shunt resistance. So, the value of the shunt resistance can be found in a very simple way. How? Because you know that the volt, that is the parallel circuit, is in fact the current divider circuit, and once it is a current divider circuit, then what happens, that the current will divide and then voltage will remain the same. Since resistances are different, right, then the current will be different, right? Why? Because V equals what? I into R. So that is, the smaller the resistance, the greater will be the current that pass through. So as the circuit is what? As the circuit is parallel, therefore the voltage across what? The voltage across the galvanometer is the same as the voltage across the shunt. So the V shunt is the same as the V across the galvanometer. So the terminal potential difference of the shunt resistance is the same as the terminal potential difference of this galvanometer, right? So what is this? It is I into R, but which I? The IS. And which R? The shunt resistance RS, like this. And what is it? This is I, and which current? The IG. And which resistance? The resistance of the galvanometer, which is known to us. Then what will be the value of this shunt resistance? The value of the shunt resistance will be IG by IS into RG, right? This RS will be equal to IG into I minus IG into RG. So this is the expression which will help you in calculating the value of the shunt resistance for your desired current I, for which you want to convert the galvanometer into the voltmeter, and the final shape of your ammeter will look like this, right? This is rather the multi-range ammeter, right? There are two range, that is one for the 100 ampere and the other for the 100 milliampere, and the other for the 500 milliampere. So this is how your galvanometer is converted into what? Into your this ammeter. Both have the same shapes and the same kind of connectivity, right? Now let us see. You can use this expression to solve the last two numerical of your this unit. Clear? Where you have been given the maximum value of the current, for which the galvanometer will be converted into the ammeter. The resistance is usually, I think, 100 ohm of the resistance of the galvanometer, and then the IG current is given, and you need to find this RS. So this is very easy, and you must remember this expression or this formula. So the value of the shunt resistance, which came out to be, is the IG into I minus IG into the RG. This is the what? This is the the value of the shunt resistance, which is the galvanometer current times the that is the ratio of the galvanometer current to that of the shunt current times the resistance of the galvanometer. Clear? So this is the conversion of the ammeter into the galvanometer. Now the next one is the conversion of the galvanometer into the voltmeter. So let us do that too. So what is a meter? What is voltmeter? In fact, the voltmeter is the modified form of what? The modified form of the galvanometer. The galvanometer, which can measure and detect higher voltage. Measure and detect a voltage or potential difference of higher value present in the circuit. So it has what? The ability to measure the potential difference or the EMF of the source with of higher value. Now how this conversion can be, that is by connecting, we can convert galvanometer into voltmeter by connecting a higher value of a resistance, a higher value resistance, a higher value resistance, a higher value resistance RH in series with the galvan, a higher value resistance RH. This is usually called multiplier. A higher value, just like in the previous case, the small value of resistance was called the shunt resistance. So a higher value resistance called what? A higher value resistance called multiplier in series with the galvanometer. In series with the galvanometer. Right, as shown in the diagram. Again, the same question which you might ask, why a higher value resistance, right? Why in series? And the third question is, what will be the value of this RH? As you usually know that a good physics always starts and ends with questions, right? So these are the many questions which we will answer down the road. Now, in order to convert the galvanometer into the voltmeter, let us just see how we do it. As I told you that we will connect a resistance of higher value called the shunt resistance. Oh, sorry, I'm so sorry. The multiplier, right? In series with the galvanometer, as you see, right? And now look, this here and here like this, and then we do it like this, and this will be the provided potential difference V. Now, because as I told you, why we will connect this in series and why a higher resistance. This arrangement of the circuit will shift the galvanometer to a different duties, like will change it into the voltmeter. Now you know that in order to measure the potential difference within a circuit, then the galvanometer is always connected in what? It is always connected in parallel within the circuit. So the galvanometer should have what? It is connected in the voltmeter is usually connected in parallel. So the voltmeter should have what? A very high resistance, so that practically no current should pass through the voltmeter. Why? If you connect the voltmeter within a circuit, for example, this is a measurement, like you want to measure this terminal potential difference, and if you connect the voltmeter, then the voltmeter is what? Since it is connected in parallel, and parallel circuit is a current divider, so this should have practically what? Very high resistance so that no current should pass through it. Right? Why? If a current passes through the voltmeter, then it will alter the current that is passing through the resistance R, and you not get precise or accurate measurement. Clear? So this is why the voltmeter should have a high resistance, and this is one of the reasons that we connected what? That we connected in the we connect a high value of resistance in series with the galvanometer. One is this. The second important point here is because you know that voltmeter is what? That you know that the series circuit is in fact what? It is the voltage divider circuit. Voltage divider circuit. So here you have what? You have the desirable range is within the maximum limit. For example, 50 volt or 100 volt, maybe depends that you are designing it for which kind of potential difference which best suits you but of larger value. So voltage circuit is what? Series circuit is voltage divider. So the greater the resistance, the greater will be the voltage to allow the same current that is passing through it. Why? Because in series circuit there is only one path for the flow of current. So current is the same. Right? So to allow the same current flow, then for the higher resistance you have the higher potential difference. Right? That is, the potential difference will be VH, and here you have what? You have the potential difference across the galvanometer VG, but this is your input, and these the terminal potential differences are your output. You cannot have your output greater than your input, the supplied potential difference. So it will be divided. How it will be divided depends the resistance. And here you have the galvanometer resistance as Rg, right? So according to the Ohm law, what is V? V is equal IR. So to allow the same current, right, within the circuit, then V by R it is. So for large RH, you have large VH drop. Greater the resistance, greater will be the potential difference. Greater will be the drop in the potential difference. The IR drop will be large. Here you have the smaller resistance, so the potential difference is smaller. So again the same thing. It will not hurt, right, in that circumstances. Clear? So let's see again the same way of scaling. Right? That first of all it will be scaled for the known maximum and minimum currents. And then you will divide the distance between those maximum and minimum value. For example, if you start with a 10 volt, so for 10 volt, and you will see where is the deflection, and you will mark that as 10 volt. And then for example, for 50 volt, you will mark that for 50 volt for known EMF source, right? And then this distance will be divided into equal parts. Clear? And that will be your desired galvanometer, voltmeter. Now let's see that what could be the value of this RH. So since you know that whatsoever is the situation here, the total potential difference will be the VH and it will be the VG. Right? Now what will be this I current? Definitely there is only one path for the flow of current, so current will be the same, right? And it will be that of the galvanometer current, IG. So what I'll be writing here is the V, and it will be equal to IG into RH, and it will be equal to IG into what? Into the VG. Into the RG. And look, the IG is common, so it will be V by IG minus, here it is plus, this is known, so there it will be minus the RG, and that will came out to be your RH. So your RH is what? Your RH is equal to V by IG minus RG. So that is the desired value for your multiplier RH. Okay, so you just see, look here, your RH purely depends on your V. Clear? Because usually the resistance of the galvanometer is known, right? And then the current that passed to the galvanometer is also known. So this is how you can convert your voltmeter into your galvanometer into the voltmeter of for measuring higher value of PD in a circuit, right? But remember, when you use the voltmeter, it will always be connected in parallel within the circuit for measurement. This is not the measurement, this is the construction. Clear? So this is all about the voltmeter. The next one is the ohm meter. Again, the ohm meter is also work in the same way as the ammeter. Actually, we are measuring the current in the circuit rather than measuring what? Rather than measuring resistance. Clear? Of the circuit. So it is just a clever way of measuring resistance using the using the current scale, right? This is very interesting. You will see here. In order to use the galvanometer for measuring resistance, how is it done? Let us see, for example, if you have, look, see here, this is just like, for example, I will just do this as this is our galvanometer, right? And we have like this kind of situation, right? And let us suppose, for example, if this is the kind of let me just provide a potential difference source, the EMF source. Here is our EMF source voltage. Now class, let us see here that what is going to be done. In fact, rather in this situation or in this case, you know class, that look, we are using the current to scale our resistance, ohm meter, right? How we can do this thing? Look, we only know that for the open circuit, the resistance is infinity. If your circuit is what? If your circuit is open, then the resistance will be what? The resistance will be infinity, right? So look, for example, here, as you see, look how I can make it infinity, like this one, right? And then there will be no current passing, and the point where the galvanometer needle stays, we will mark that point as infinity, for example. Now look, then what we will do for the next one, that is the short circuit case, for example. Look, when we short circuit, like just directly connected, then there will be what? There will be a conducting path and the resistance will be least, and the galvanometer needle will give you a full scale, full sort of deflection for that value of, and we will note it down, that current, and that will be the desired resistance, and the known resistance will be calculated for that shunt value. And let us suppose, for example, it could be that is the for infinite resistance, okay, and we will mark that like here. And now we will do this for known resistance, and we will replace this as for the known resistance, right? And definitely for the known resistance, there is no we will mark it as 0, right? Why? Because if you just make a short circuit, then what will be the resistance of the path? 0 ohm for the maximum current of the galvanometer, right? Maximum current will pass through the galvanometer, and since it is short circuit, right, there is no resistance, and we will mark it as O. Now let us do it for what? For known value of resistance, any resistance or variable resistance. Now if this resistance is known to me, then definitely the galvanometer needle will point somewhere between 0 and infinity. Let for example, if this is 50 kilo ohm, yeah, mega ohm, so the galvanometer needle will be somewhere here, for example 50 mega ohm, and then this distance will be then divided, right, into equal parts, and then we will scale it this between infinity and that maximum value. So this is very easy. Now the next one is the aometer. Now what is the aometer? The aometer is a device in which you will see all in one: aometer, ampere, volt and ohm. So it measures all together, right? Let me check this. Where is meter? No, it is not. Yeah, maybe it might be somewhere there. In the voltmeter, let me check. The volt, the ammeter. Class, it is not on my, right now it is not on my radar, but in the electronics cupboard it might be somewhere. Okay, but there are two important things. That is the two important points where you would know about this. There is what? There will be the function selector first, the function selector, and then within the function selector there will be the range selector. The range selector. So it is a multitasking device for the function selector. For example, whether you measure current, whether you measure potential difference, or whether you measure the whether you measure the resistance ohm, which one you are measuring. So the function selector should be first adjusted and set to that on that physical quantity, for example for current or voltmeter or ohm meter, and then there is the range selector. So this is the range selector and this is the function selector. So for the range selector, for example, if you choose A, you are measuring the current, then within which range, whether your current is in the milliampere range, for example 10 milliampere, for example 5 ampere, and for example you are measuring a current even higher value than this, then it will be just the range will be shifted to that particular point. So an aometer do all the things together, but remember, you can just measure one thing at a time. It is not like this that they will it will tell you all together. No, one, if you want to measure n meter, then at the same time it can only measure current, not the voltage, right? So you should keep this point in your mind. And then there is a digital meter also. The digital meter, that is more easy to use, right? And you can quickly read the required measurement on a screen, which will display you in the form of a number like 2 ampere or 3 ampere. So digital meter is more modified form, and we can use that very conveniently and easily rather than using the analog kind of meter. So this is our today lecture. Thank you very much, and most probably this is the end of the unit number 13, I think, electromagnetism. So inshallah we'll see you in the next lecture, and that will be the electromagnetic induction. That is also important. So in our today lecture you have learned about the conversion of galvanometer into ammeter and to voltmeter, and then into the ohm meter, and then the ammeter. The most important point here is that how we can calculate the shunt resistance, why the shunt resistance will be of smaller value, and why it will be connected in parallel with the galvanometer to change it into the ammeter. All these three questions I answered, and I also told you that an ideal ammeter might have zero resistance so that all of the current should pass through it when it is placed in a circuit. For the voltmeter, I told you that when we convert the voltmeter, the galvanometer into the voltmeter, then a multiplier will be connected in series, and the multiplier will be of higher value resistance. And then I told you why a higher value resistance, because voltmeter is connected in what? In a parallel within the circuit for measurement. So ideally it should have a large resistance so that no current, practically no current pass through it, so that it should not alter the current that is passing through the resistance or device. So this is why ideal voltmeter might have a higher resistance. And then for the ohm meter, I also told you, and I told you that it is the kind of technique that in fact the using the ohm meter we are just deceiving our galvanometer, right? We use the galvanometer, which is current measuring device, and we use that device to measure the resistance. And I told you about that clever technique, that how we are doing it. And for the ammeter, that is all in one. So Allah Hafiz, thank you for this.